Hello. Okay, so we are in the week 12, and it is the last week of the course. So I hope you have watched the lectures. So uh, I think I'll just introduce myself. My name is Syed Shabir Ahmad, and I'm a PMRF scholar in IIT Madras, Department of Applied Mechanics and Biomedical Engineering, IIT Madras. And you are asking about the upcoming exam. So I think you have watched all the lectures and
Yes, sir.
yeah, and you have attempted all the assignments, right?
Yes, sir.
Yeah. So the kind I mostly the kind of questions you have seen in the assignments, uh, you will get to see in the exam too. So it's not a like it's not a big problem. So you have to be very thorough with the concepts, especially everything which was taught in the class, and also uh, things like questions will be not very lengthy kind of questions, like you have seen what you have seen in the assignments. Those kind of questions, like you may get a question with the four or five. You may get a single description and 4, 5, 6 questions on based on that. Those kind of questions, and so yeah, obviously you have to be very careful about the things which are asked in the questions, like units. Uh, Units should be consistent. Like they may ask you in the question they might have given in SI units, and they may ask you the answer in some other units. So be prepared for those kind of little bit tricky things, like those which can confuse you. So I think most of the questions are I think they're uh, these questions, like numerical type questions. So you have to enter the answer. So there will be a particular range. So if like it's not like you have to get a perfect answer. So like if you get the answer nearby due to rounding up, some errors will be there. Those will also be taken care of. So you don't need to worry about like I have to get a perfect answer. Like you don't need to take 10, 20 decimals and do the answer and all. So and I think you have to deal with. I don't know if you are allowed with. Your calculator is allowed in exam. Maybe you have to use the digital calculator which comes in the computer. So go through the rules and regulations and see if you have to use the calculator. Already, if you are comfortable with the calculator which comes in the exam, then it will be fine. Otherwise, you can uh, uh, download that. You can get that calculator anywhere. So in Google Play Store, some kind. Also, you can get the calculator. Like you can, I think that the same calculator comes in Gate, so you can search Gate calculator like that in Google Play Store. You will get the calculator, and so get used to that calculator. Maybe that will be useful for you. Uh, Other things are like yeah, some lot of multiple correct answer type questions will be there. So like you can get 4, 5 question, 4, 5 options, and out of that 2 to 3 maybe right, something like that. So those kind of questions would be there. So I think that would sum up neatly like whatever which will be asked in the exam. If you have any doubt, you can ask me.
Topic-wise weightage.
Topic wise weightage is not. I don't think we don't have any. I don't have any information because Uh, there is no such thing. Depends on like whatever has been taught. Uh, I don't think there is a weightage or something like that. So you should not expect that this topic will be asked more or something like that. So you have to be prepared for everything.
Okay, sir.
Where are you from?
I am from Bihar, Bhagalpur College of Engineering.
Okay, which year are you in? Which year of engineering?
Second year, third semester.
Okay, okay. Did you attend any sessions before? Here, no? Uh,
यस सर, फर्स्ट सेशन
okay,
बीच में
okay.
सर नहीं कर पा रहे थे सर, क्योंकि यहाँ सर क्लास हो रहा था, एग्जाम भी चल रहा था.
ठीक है, okay. Okay, we'll start today's session. So this week uh, was entirely focused upon basically we continued from the last week um, failure theories, uh, different kinds of failure theories, and then we went on to stability. So stability of columns, what is critical load, and all those things. So these were the main two things which were discussed in this week. So and like
Hi, sir. Good evening.
yeah, good evening, good evening. So these were the main two things which went upon discussion in this week, and we'll see some things like um so we saw like failure theories. There are different kinds of failure theories based on the material, like the based on the nature of material, like brittle or ductile material. We may be compelled to use different failure theory. So, like there is maximum principal stress theory. There is maximum shear stress or Tresca yield, I guess, theory. Maximum shear stress, Tresca stress theory, and there is also maximum distortion energy theory or von Mises theory. And then we also saw more Coulomb theory, more Coulomb failure theory. So I guess these are the main ones which are discussed. The first and last ones are basically for brittle materials, and the second and third ones are for ductile materials. So, so what are failure theories? So, failure theories are some things like these are like things which you can use while designing any structure. So the thing is, mm, when we design a structure, we don't have any like experimental results or something, because we don't have the structure itself. We have to design it and then make it. So what we can do is like we can take a small specimen and we can conduct the tension test. So by conducting the tension test, we can get the yield stress of the material. So then after that, we can use this uh, failure theories and make sure that whatever the stresses which we get are under the prescribed or the prescribed stresses, like for brittle materials, uh, it should be lesser than mostly the maximum shear stress or something else. So it use boundaries in which your stresses boundaries are what you can say limits to your stresses, so that it doesn't go beyond those limits, and eventually it leads to the failure of the structure. So failure of the structure or the material. So depending upon, as I've said, different criteria and also different kinds of materials, brittle, ductile. So different failure theories have been proposed. So it doesn't mean that these are very theoretical ones. Like it doesn't give you a true or a exact uh, thing which occurs in the experiment, but it will give you some limit, so that uh, you can uh, what you can say predict, or you can avoid the failures. So if you stay within those limits, you can avoid the failures most probably. Yeah, but the true results can be given only, the true failure can be explained only through the experiments. Though these are only, you can say, like a kind of a prediction or substitute to the experimental thing. So these things you can uh, learn even more when you go to your advanced courses, I guess. Um, Maybe in design parts like machine design or something else, like if you are from mechanical engineering. So apart from this, there are some other theories also, like maximum strain energy theory, maximum octahedral shear stress theory is von Mises only, and we have maximum distortional strain energy theory, like that. So let's see. Uh, so let's see what do you remember, kind of thing. So when the minor principal stress sigma 3 is 0, uh, and sigma 1 is not equals to sigma 2, the von Mises yield surface takes the shape of what? What shape does the von Mises yield surface take? Shape of, yeah,
Sir, it is elliptical, sir.
yeah, exactly. So we have seen that sigma 1 on this axis and sigma 2, and we take sigma 3 is equals to 0. So we assume we take sigma 3 is equals to 0, which is the minor principal stress, and the yield surface will look like this elliptical motion. This is for one Mises. This is according to one Mises theory. In case of Tresca yield theory, what does the surface look like?
Sir, it is look like not exactly hexagon, but inside it
Yeah,
it is a line.
yeah, it is a hexagon only. It has six
Yes.
sides, not like a hexagon. It is a hexagon. So it
Yes, sir,
looks
but
like this.
no,
Yeah,
no, all sides are not equal.
yeah, all sides are not equal, just a hexagon. So this is Tresca yield surface. So uh, let's see a problem maybe.
Sir,
Yeah,
I have one doubt that I forgot what you mean by statically indeterminate or statically determinate. What you mean by that, sir?
statically indeterminate or statically determinate. So if you have any structure or a structure, like let's say like a beam, I have, let's say this is a beam, this simply supported beam. Let's say I'm applying some load on it, something like this. So I have because this is a 2D structure, I'll get three equilibrium equations, right? Three equilibrium equations, that is sigma fx equals to 0, sigma fy is equals to 0, and sigma mz equals to 0. These are my three equilibrium equations for a 2D surface, for a 2D structure. If this was a 3D structure, I would have got six equations.
Okay, sir.
Okay, sigma fz is equals to 0, and sigma mx equals to 0, and sigma my is equals to 0.
Yes, sir.
For this structure, I have three reactions. You can see this is a pin support. I have, let's say, this is A and this is B. This is RA and let's say HA, and this is RB. So I have three unknowns. Okay, three unknowns or three reactions. Three unknowns is the thing. So I have three equations and three unknowns. Using three equations, I can I can solve for three unknowns, right?
Yes, sir.
You know algebra, right? Like you have uh, three equations: ax plus something a1 b1 plus c1z, a2z plus similarly a3. So there
Yes, sir.
are three equations and three unknowns. I can find out the using three equations. I can solve three equations, and I can find out what are these unknowns. Like in this case, x, y, z, or in the beam case, that is R A, R B, and H A. So three equations of equilibrium and three unknowns. So I don't need any extra equations. So that's why this is called as a statically determinate structure. So for the problem is called statically determinate problem. Okay.
Okay, sir.
Okay. Now, if I take, let's say, a cantilever beam like this also has one second. So this also has three unknowns, right? I have VA, let's say this is A, and let's say this is pre end is B, and this is HA, and I have moment at the end, fixed end. So there are three, and also there is some load. So there are three unknowns, and also we have, because this is a 2D structure, we have three equilibrium equations. Okay, so using three equilibrium equations, again I can find out what are these three unknowns. So I can solve for three equations and find out what is HA, HB, HAVA, and MA. A
Yes, sir.
simple cantilever beam is also a statically determinate beam. Let's say I have a prop at the free end like this. Say I have a prop. I have a roller at this. This is called as a propped cantilever beam, right?
Okay.
So now you are getting additional reaction, which is RB, or let's say okay RB only. So additional reaction RB you are getting. So for this structure, we have four unknowns. Four unknowns are there. So which is VA, HA, PMA, and RB. But we do not have four equilibrium equations. Okay, so we can only have for this 2D structure, we have only three equilibrium equations, which are again like sigma HA and sigma VA equals to 0, and sigma Fx is equals to 0. What am I writing? Sigma Fx is equals to 0, sigma Fy equals to 0. Horizontal force, sum of horizontal forces should be equals to 0, sum of our vertical forces should be equal to 0. Like that, if I take and moments, sum of all the moments should be equal to 0. Then I can say that if all the equations are satisfied, then I can say that structure is static. Okay, structure is static. That's why the name static comes. Means the structure is not moving. It is at a single place. It may deform, like it may bend or it may expand, but it is not moving. That's why it is static. Okay. So these are static equilibrium equations. Three static equilibrium equations. So I have four unknowns and I have three equations. But it's not possible to find out uh, four unknowns using three equations. So we should have some one additional equation, right?
Yes, sir.
So that's why if you remember, we have done this problem in deflections. So
Yes,
where
sir.
we take another equation called as a compatibility equation. Okay, compatibility equation is nothing but the deflection caused by this the deflection caused by the load and the deflection caused by this reaction should sum up to 0. Okay,
Okay, sir.
yeah, the deflection caused by both the things should sum up to 0. That is one compatibility equation. So compatibility means it is giving you some condition about the displacement or rotation, something that kind of thing. So using that condition, you can find out what is RB. Hmm? Okay, then you can find out. Then we are left with only three equations. Then we can find out three unknowns and three equations. We can find out remaining series. So if the number of unknowns are greater than number of equilibrium equations, these structures are called statically indeterminate structures. Okay, means
Yes,
you
sir.
cannot find out the all the unknowns only using the number of equilibrium equations. You need additional conditions to satisfy these equations. In real life, most of the structures are statically indeterminate. Like they will have a lot of other constraints. Statically indeterminate structures are more safe because you have additional support, right? Like this cantilever beam has a more has a roller, uh, has an extra roller, uh, which is supporting, and it is also due to this roller, deflection is also getting avoided. So if I have instead of the roller here, I can also fix this end. That then you will get additional three reactions. So it is like more statically determinate than this. So you need three conditions more. So two conditions more, like you can get RA, VA, and MB. So fixed beam. That is also a statically indeterminate. So these are more safe in terms of these are more what you can say. It's not safe, like more strong, uh, uh, more stronger than the statically determinate. But these are the in terms of analysis, it is difficult to analyze these statically indeterminate structures because simply using the equilibrium equations, we cannot solve for these unknowns. So we have to get extra conditions. Uh, then we can do the analysis.
Understand, sir.
Yeah,
Sir, another thing that, so
yeah,
whatever we study the all about the beam, we
mm.
consider all our slender member. But
Yeah. We consider all the cylinder.
sir,
Yeah.
but actually, whenever you see the bridges and all are the from end are
Mm.
it is thick, and but when it is go at extreme end, that is very slope. Means I need to tell when sorry cantilever beam type when the metro rail station and all are end is it is big thick and broad, but when it is go middle toward it is slant.
Okay, okay, okay. Yeah,
So
those are things like tapered sections you are saying.
yes sir.
Yeah. So those are very like uh, those are the things which you have to take care in design because you don't want like let's say like uh, uh, in the middle we don't need that kind of uh, material at the supports we need extra material because there will be like what you can say a lot of shear at the supports in the middle only there will be bending moment so things like those you can consider like depending upon the analysis of the structure like if the bending moment is more you have to uh, uh, you can remove the material if the only bending moment is there you can remove the material if there is like shear force if the uh, shear force is more at the ends then you need more material more cross section at the supports things like this you can do
Understand, sir.
yeah so I don't know if you study all those things I guess you study I have because I haven't taken machine design maybe you get to encounter these things paper sections how we design and all those things those are what you can say design decisions because you want to reduce the cost and material of the structure and also improve the efficiency those kind of decisions accordingly you have to make okay
Okay, sir.
let's say uh, a force of over 45,000 newtons is necessary to rotate a shaft at uniform speed and the shaft is made of Young's modular elastic sorry ductile steel whose elastic limit is okay elastic limit means yield stress is 207 MPa. This is the yield stress of this material of the steel which is used in the shaft, both in tension and compression. And E is also elastic. Sorry, Young's modulus is also 207 gigapascal, and Poisson's ratio is 0.25. Okay, and the shaft is something like this. We have a shaft. something like this. This distance is 15 centimeters, and this is the force which we have to apply to rotate this shaft, which is given as 45,000 kilometers. And we take a point or the section at A, point A, which is at a distance of 20 centimeters from this free end of the shaft. Okay, so first we have to uh, determine dia using octahedral stress theory. Octahedral is also, you can say, 1s stress theory. And the maximum shear stress theory. Maximum shear theory is also called Tresca yield stress theory. And we have to use factor of safety n. Factor of safety is equals to 2. Okay, that we have to use factor of safety as well. So let's calculate what is the bending moment and also what is the torsional moment due to the applied force on the shaft. So the bending moment is basically force into distance up to this, that is 20 centimeters. So I have to convert that into meters. So force into the distance 45,000 Newton into 20 by 100, just converting the centimeters into meters, and I'll get this as 9,000 Newton meter or 9 kilonewton meter kind of. Torsional moment, I'll get F into this distance 15, or you can say 45,000 newtons into 15 centimeters, which is 15 by 100. I'll get this as 6750 Newton meters or 6.75 kilonewton meter. Okay. So let's find out the bending stresses. So bending, we'll go to the bending part. So we have in order to find out the bending stress, we have the bending formula, which is flexure formula, which is sigma by y is equals to mb by izz. So since the cross section is a cylinder or a circular cross section, I get izz equals to pi d power 4 by 64. This is my izz. So sigma b is equals to, so we generally take uh, minus, right? So sigma b into sigma mb into y by izz. So I know mb, which is 9 kilonewton. I have, let's say I'll convert this in kilonewton meter into Newton mm. So that's why I'm multiplying it with 10 to the power of 6. And why the maximum stress occurs at the outer surface of the top and bottom of this, uh, or you can say at the maximum distance from the neutral axis. So that's why I take y is equals to d by 2, and I have pi d power 4 by 64. So, so if I do this, I'll get sigma b is equals to minus 32 into 9 into 1 second. Huh. Lot of spam calls these days. So we'll get, we don't know that, let's say, like we'll find out. So this is the bending stress we get using the bending formula. Let's now find out what is the shear stress due to the torsion. Uh, Shear stress due to torsion. So we have the formula for torsion, which is tau by r is equals to mt by ip, which is the polar moment of inertia. So we have tau, or you can also, we can also say this as tau r theta. Can say tau, whatever. We have this as 6.75 kilonewton meter. So I will convert this into Newton now. Again, so R is maximum distance. So at the extreme, the periphery of the cross section, we have the maximum shear stress. Here the polar moment of inertia is pi d power 4 by 32 instead of 64, which we get because this is the polar moment of inertia. So I'll get shear stress as 6.75 into 10 to the power of 6 uh, into 16, let's say, divided by pi dq. This is my shear stress. So we are taking a point at a distance of 20 centimeters from the free end of the shaft. And on the point, if I take a small element, so it will look like this. Let's say this is z direction and this is r, and we have theta, so which is the, can say, polar coordinate system, r, theta, and z. So if I take a small element on here like this, if I take this, so it will have this bending stress, and we'll have the shear stress due to the torsion. So these two stresses are experienced by the shaft. This is tau r theta, and sigma b, you can say I will take as sigma z also. Okay. So now I have to get the principal stresses. So the principal stresses sigma 1 or sigma 2, sigma 3 can be say sigma 1 plus sigma 1 plus sigma 2 by 2. But here you can see that sigma xx plus sigma yy by 2, right? Here we can see that I have only one normal stress on this element, that is sigma b. So that's why sigma b by 2 less or minus uh, root over sigma b by 2 whole square. This is sigma 1 minus sigma 2, sigma 1 minus sigma 2 by sigma 1, sorry, sigma xx minus sigma yy by 2 whole square plus tau xy whole square. So here instead of that we can say this tau square. So for this element, these are the principal stresses. After substituting whatever I have got tau and sigma b, uh, say sigma 1 I'll get as sigma 1 I'll take plus, so 16 into 9 into 10 to the power of 6 by pi d cube. So 32 uh, will become 16, so plus uh, root over 16 into 9 into 10 to the power of 6 at pi d cube whole square plus I'll get this 16 into 6.75 into 10 to the power of 6 at pi d cube whole square. So this is my major principal stress. So I can take out D from this and root from this root. I can take out D cube, or you can say I can take out 1 by pi D cube. And also 10 to the power of 6 I can take out 10 to the power of 6 by pi d cube, and I'll remain with the other thing 16 into 9 whole square plus 16 into 6.75 whole square. So, so if I do the simplification, I'll get you can say 1 by pi d cube. From the whole thing, if I am taking 1 by pi d cube into 10 to the power of 6, I'll remain with this 16 into 9 and root whatever the value of this root, which comes out to be 180, and I'll get sigma 1 is equals to 36 into 10 to the power of 6 divided by pi d cube. This is sigma 1. And similarly, sigma 2, sigma 3 I'll get instead of plus here I have to put minus. Everything will be same. So I'll get 1 by pi d cube into 10 to the power of 6 minus 16 into 9 minus 180. Sigma 3 I'll get 1 minus 1 by pi d cube. 324 into 10 to the power of 6. This is my sigma 3. So I have got the principal stresses, sigma 1 and sigma 2. Let's find out what is the maximum, let's find out the diameter using the various theories which we have. So first, so we have the structure, and the structure is subjected to some load. So we are going to design the structure. Designing means we have to find out the dimensions of the structure so that it doesn't fail. So we don't have the actual structure, so we are just using this theory such that whatever the bounds are there for the structure to fail should not be crossed, and the dimension should be uh, in that range. So let's find out the diameter first using the maximum shear stress theory. So this problem you can also see that we have take this is a combined loading problem. We have taken torsion and also bending. So and two effects are taken. So and also remember that whatever we are doing here is linear analysis only. So it's not non-linear thing, so that we can directly sum up the effects due to shear and uh, tor- torsion and bending and all those things. So feasibility of this is due to the linear region of stress strain curve which we are assuming. We are in that linear region only, so we are not going beyond that. So so they have given that factor of safety is 2, right? So according to the maximum principles, maximum shear stress theory or Tresca yield criteria, we get this. So sigma 1 minus sigma 2, sigma 3 by 2 should be less than or equals to sigma ys by 2. So yield stress by 2. So since they have given the also given the uh, what do you say factor of safety. So factor of safety is uh, I'll just multiply this with the factor of safety, or factor of safety you can say n here. So factor of safety is nothing but the design stress, the permissible stress divided by allowed stress. So which is sigma ys by sigma 1 minus sigma 2. So like you can say this is the factor of safety, sigma ys by sigma 1 minus sigma 2. So if I multiply, uh, so we are making sure that we don't go beyond like we are remaining well lesser than the yield maximum shear stress which can occur, because there might be other effects to uh, other effects also, like see in the we cannot see in the analysis or design stage. So there might be some other yes, effects due to the material defects and all those things. So we cannot predict everything that happens in the external. So we make sure that uh, it is lesser than what is lesser than what is the maximum shear stress, uh, very much lesser than maximum shear stress using the factor of safety. So so factor of safety is given as 2, and the other things I have sigma 1 and so 2 I can say let get cancelled here, and sigma 1 is I've got 36 into 10 to power of 6, and I can remove 1 by pi d cube minus minus and minus, which is like let's say minus of minus 324 is less than or equals to 207 by 2. So everything is units are consistent. I have taken everything in Newton mm. So megapascal is nothing but Newton mm. So now I can do the calculation for this thing, and uh, I can send pi d cube. I have d cube here on the right side, and if I do this, I'll get uh, 360 into 2 divided by pi into 207, and it's less than or equals to d cube. Okay, so now if I take the cubic root of this, I get d should be greater than or equal to 103 0.5 mm. Okay. So using the maximum shear stress theory, I get this diameter. Let's say if I have not taken the factor of safety, things would have been different. I would have got the diameter more than what, like, I would have got more closer to uh, like diameter would have been less, and my failure would be you can say reaching the maximum shear stress. But here we are using the factor of safety. Let's say this is the shear stress curve. This is the yield stress. Let's say by using the factor of safety, we make sure that we go to here only. So we don't go beyond this, because there might be other effects which we might not see in the experiments and all. So that's why using the factor of safety, we take the limit less, uh, you can say maximum allowed stress lesser than the yield stress. So that's why the diameter is 103.5 mm. If I haven't taken the thing, then my diameter would be lesser, you can say. Yeah.
Sir, without factor of safety, the diameter is 82.109.
Yeah. Okay. Yeah. Yeah. Then it's fine. So, like, if we diameter should be greater than this, so that we don't go beyond the permissible limits. So failure is avoided. So this is how we do the design using the shear maximum shear stress theory. Let's go to the other theory, which is actual octahedral stress theory, octahedral shear stress, or maximum distortion energy, whatever we can call it, or von Mises theory. So this is nothing but we get this expression sigma 1 minus sigma 2 whole square, sigma 2 minus sigma 3 whole square, plus sigma 3 minus sigma 1 whole square, is less than or equals to 2 sigma y s whole square. So this is the octahedral shear stress theory, or one Mises theory. So since there is a factor of safety given, I have to multiply this factor of safety on the left hand side, so that I get more protection, or I can reduce the allowable stress uh, to avoid uh, effects due to the other things. So I can that can be those can be taken care of. So I get sigma 1 only, sigma 1. There is no sigma 2. Sigma 2 is 0 in this case, and sigma 3 square, and we get sigma 3 minus sigma 1 whole square. Get 2 I can cancel, so on the right hand side and the right hand side. So I'll get sigma 1 square. So what I'll do is I'll remove all the square terms. Uh, I'll get 1 by pi d cube into 10 to the power of 6 whole square. I'll remove. I'll have 36 square plus 324 square, 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 plus because this minus comes back. And I have minus 324 minus 36 whole square. And I will have 207 square. So if I send this 207 here, pi square into 207 square, at dq. So this thing is 36 square plus 324 square plus 360 square. At 235872. Okay. And into this 10 to the power of 6 is pi square into 207 square. I'll get 5.774 534 36 into 10 to the power of 11. Okay. So if I do the cubic root of this thing, get getting something up.
Sir, my calculation got wrong in between. I check again.
Okay, okay. Okay, okay. Okay. This is d power 6, sorry. Okay. Something down again.
So it is coming negative, sir.
Negative. How it?
Negative means it is too small. 8.29 into 10 to the power minus 3.
10 to the power of minus 3. No, something is wrong. See, this you have got 436 into 10 to the power of 11. I'm getting it should be greater than 90.7275. Yeah, see the calculations.
Okay, sir.
This is according to the maximum shear stress. Sorry, after shear stress. Got it?
1 minute, sir. Just.
Okay, okay.
Yes, sir.
Got it?
Yes, sir.
The same answer?
Yes, sir.
Okay. 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 So Priyanka has joined. I'll briefly explain what we have done.
Sir,
So,
I have wondered.
hmm,
So here the force is acting, so we also take the another moment also there, na? So when we transfer the force to the this big shaft,
yeah, yeah. See, that's why that's why we have got the bending moment and also the torsion moment, right? See, this is something, and you are applying the force here. Okay. So we are not designing. Let's say this. Uh, we are not designing for this. Forget this. Okay. I will just, or you can say this is very short compared to this. Let's say this is something, and there is some lever kind of thing, and you apply the force here. Okay. So to rotate the shaft, and so this is the distance d. Okay.
yes, sir.
So you are shifting is here. So I have the force
Yes,
and the
sir.
moment, which is the torsional moment. Okay.
Yes, sir.
Force and moment both are there. Torsional moment is also there.
Understand.
So due to this force, bending will occur in the shaft, and torsion moment is anyway there. So let's say if I had a shaft like this, and I am applying force like this. Basically, I am applying a couple. Then I won't get. Then I will get only torsion moment because I
Yes, sir.
have shifted these two forces. I will get net force 0 here. So I'll get only the torsion moment. Okay. So this will not have any bending effect, but this will have a bending effect.
Understand, sir.
Okay. So what we have done is, I'll just explain again because Priyanka has joined just now. So there is a shaft uh, which is like this as shown in this figure, and you can say that uh, 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 it is being applied by a force at the free end, which is 45 kilonewton, and maximum permissible, or like not maximum permissible, the yield stress of the material, which is steel, is given, that is 207 megapascal, and Young's modulus, Poisson's ratio, everything else is given. So we have to design this shaft. Designing means length, everything is, let's say, known. Only diameter, everything is fixed. I have to design the shaft. So only unknown is the diameter, which I have to find out here. So for design, we have to use the failure theories. So failure theories are the ones which give the uh, you can say bounds for the uh, maximum allowable stress, so that whatever force we apply, due to that the stress should not go beyond the allowable stresses. So if the stress due to the applied forces go beyond the uh, allowable stresses from the various failure theories, then we consider that structure or the material is failing. So we don't want the failure to happen. So we take uh, this failure theories uh, into consideration, and we design the shaft here. So shaft here, we using that we can get the diameter of the shaft. So as I have said, there are two things which happen. Uh, One is twisting and also the bending due to the nature of the applied force. So first we find out the bending stress in terms of the diameter. We don't know what is the diameter. We'll find out at the end. And then we find out the shear stress due to the torsion. So due to torsion, there is shear stress occurring. So here we use the bending formula, and again to find out the shear stress, we use the torsion formula. So, and using both this, uh, the element, the stress on the element of the shaft will some element on the shaft will look like this. There is a bending which is happening, which occurs in the z direction. Bending stress will be occurring in the z direction, and we have the torsional shear stress, which is tau r theta. So so now we can find out, we got the stresses uh, uh, which are occurring on the shaft due to the applied force. And now we have to find out what are the maximum and minimum principal stresses. So we know sigma xx plus sigma y by 2 plus or minus root over again whatever everything. We have learned this in more circular the other chapter. We use that, we determine the maximum principal stress in terms of d and the minimum principal stress in terms of d, and we don't know what is d. So now we go to the uh, failure theories. Using the failure theories, we determine D. So first is the maximum shear stress theory, which we use. Uh, that can also be called as like Tresca yield criteria, whatever. So I am applying. I'm using this expression and also multiplying with n, because the factor of safety is also given. So factor of safety is 2 here. So sigma ys by sigma 1 minus sigma 3 should be equal to 2. So everything we substitute sigma 1 and sigma 3, and we know sigma ys, which is given in the data of the problem, and we determine that d should be greater than or equal to 103.5 mm. So if this d diameter is greater than this thing, so we can say that according to this maximum shear stress theory, material of the shaft would not fail, and it will remain well safe, well within the bounds of the allowable stress. Then we go to the octahedral shear stress theory. This is also, remember that these both the theories are applicable for ductile materials. So steel is a ductile material, so we are using both these theories. So this, as we have discussed in the last week, also that this theory, octahedral shear stress theory, depends upon the distortion energy, or the distortion, or you can say we have hydrostatic stress tensor, and what you can say the other stress tensor. We divide it, and we remove uh, the hydrostatic stress, and we take only the uh, stress which gives us the distortion. So they observed that this is the um, main stress, or the octahedral stresses, or whatever things. These are the things which are contributing. So instead of the maximum shear stress, we are using the energy of the uh, you can say the strain energy here as the failure criteria. So, and we are making sure that this energy due to the distortion of the element is lesser than the uh, strain energy when we apply this uh, when we do not strain energy due to the uh, yield stress when we do a tension test. So we substitute again everything, we get the diameter as uh, greater than or equal to 90.725 mm. So the as you can see that in the maximum shear stress theory, uh, we can see the diameter is higher than that of what we have got in the octahedral shear stress theory. So this we can also explain using this diagram. We got the sigma 1, sigma 2 yield surfaces we got, right? So the yield surfaces. This is for the Tresca yield criteria yield surface, assuming sigma 3 is equal to 0. So whereas if I go to whereas if I use the octahedral shear stress, I'll get a ellipse. So you can see that it has a little bit more. It allows more. It allows a little bit more stress. So you can say. So that's why if I have the diameter a little bit less also. So if I have the diameter less, it means the area is decreasing and stress will be more. So that's why uh, you can say that using the maximum the octahedral shear stress theory will save me material. So I can use a lesser diameter rod compared to the maximum shear stress theory. Okay. Next, we'll move to the other part which was discussed in this week. That is about the columns. Okay, stability of columns. So yeah, anyone wants to speak?
Sir,
Yeah.
sir, like we transmit the power through the shaft in the horizontal way. So in the
Mm.
horizontal position. So say so in some this oil hole drilling and all these cases where the shaft are vertical, sir.
Mm.
So in that time, so this buckling load are considered plus the torque also considered there, na sir?
Yeah, yeah. Everything which occurs, you have to consider everything. Torque, all the things you have to consider. Torsion, whatever the effects which may occur, you have to
Okay,
consider
sir.
everything, and you have to do the design. So that's why we have seen that um, uh, initially we have learnt everything as a individual thing, and then like now we are combining everything like torsion, bending. You can also have sometimes axial loads, tension, compression. Due to the compression, buckling happens. So compressive loads.
Understand, sir. Sir, I also seen one photo when the professor showed to us that
Mm,
the one beam is fully bent. So,
mm.
say in your civil construction, sir, how much factor of safety you could means go for if you it bridge and all, or if it is a house and if it is dam. So, generally, the factor of safety I think very huge.
Yeah, factor of safety for civil engineering uh, civil engineering structures is very huge because we don't want structure to fail, and also we don't want the structure to deflect. So deflections also should be very less because it will not be serviceable. Like you cannot have a bridge which is like bent like this. So that should also be very less. So as far as the factor of safety is concerned, like there are like two different things. Like one thing is we construct only this RCC structure. So RCC structures will have different factor of safeties, uh, and there are also steel structures. So RCC structures will have more factor of safeties because concrete is a very complex material. So concrete and steel. Reinforced concrete means concrete in and also with steel revers we use. So it is a very complex structure, and while casting, there are a lot of defects which might happen. Compaction, concrete might not be compacted. So in that case, we take factor of safety a little bit more. And while we go to steel structures, because we are already using the prefabricated sections which we get from the manufactured plants, manufacturing plants or steel plants. So we can reduce the factor of safety and save material. So depending upon the nowadays, you can see the metro constructions, everything uh, which are happening. Uh, they only cast the pillars on the location. Uh, Only pillars are constructed at the location of the site of the metro. Everything else, the girders or the bridges, which you see, they precast them, and they uh, they bring them from the other side, manufacturing plant. There will be a manufacturing plant somewhere outside the city. They'll put a plant, and those girders or the bridges are constructed, and then they transport it from there, and simply they'll fix it on the top of the pillars which are constructed. So if I am doing this in a manufacturing plant, I have greater control over the quality. So I can utilize, you can say, lesser factor of safety, and I can save material. I have the things which I can control are more when I have a manufacturing plant. Whereas in the site, there are a lot of factors which are not in control. So depending upon those things, factor of safeties are there. So uh, I don't know about mechanical engineering. So, but if you go for civil engineering structures, so civil engineering for steel and yeah, this is also for mechanical engineering also. So we have the Board of Indian Standards, right? So for everything, they have prescribed the factor of safety limits, whatever we have to follow. So according to that, we design. So we have to make sure that we follow the guidelines, because these design booklets will be there, right? So design booklets, so you have to follow all the criteria. uh, then only you get the approval and all those things for the construction, whatever you are making. So design criteria given, like uh, for India, there is BIS, Board of Indian Standards. Like you go to US, there is ASTM or AST, ASME. So different organizations or different countries have their own design guidelines, which you can see in their design books or something else. So uh, you have to use them, you have to follow them, so that we can maintain consistency, and we can avoid failures of the structure, all those things.
Understand, sir.
So we have seen that stability also, the stability is a concept which I have learned here. So we say a structure is stable when the mm, uh, derivative, or you can say second gradient of the potential energy is greater than zero, and we can this is stable. And if we have this equal to zero, then it is neutral. This is stable equilibrium, this is neutral, and if this is less than zero, this is unstable equilibrium. So unstable equilibrium. So we want the structure which we are designing to be stable, should not be unstable. Maybe it's neutral or stable equilibrium, but not unstable. So these things you might um, this derivative and all, this kind of explanation, if you go for masters, maybe I don't know if you study these things in graduation stage, undergraduate stage, like if you study variational principles and variational energy, uh, those kind of courses, you can get to know more about these things. For now, you can just remember what this expression is. So the buckling failure is happens only to the columns which are long and slender. So long and slender means the cross section is cross section dimensions are small compared to the length of the beam or the column, you can say. So if I have a column like this, uh, the column dimensions are comparable to the so the cross section dimensions of the column are comparable to the length of the column, then we don't see buckling. Only in the long and slender columns like this, length is high but the cross section dimensions are small. In this kind of columns, we can see buckling. Here we can see just you might have seen the lecture in which professor showed a concrete column, just
Yes, sir.
what do you say, crushed. That is called just a crushing. So buckling happens in the long and slender columns. So
Sir, in construction or otherwise in any other thing also we use hollow beam.
yeah, we do use hollow beams, like especially in not in concrete constructions, concrete structures. In steel structures, you can see a lot of hollow sections. In concrete, you might no, we don't see. Like it's difficult to do correct cast and do things also.
Okay, sir.
Steel sections like have seen, right, like circular sections. You can see poles, different things. Mm.
Yes, sir.
So if I have some if I have some column like this, column or strut, whatever you can say, and some load is some load I'm applying. You can say this is a strut test. So only difference between column and a strut is like in struts can be in various different directions, but column is considered to be having a column is in vertical direction. But the columns and struts are basically the members which take compressive loads or which experience compressive stresses. And this is L and this is D, and I have this cross section of this column as strut as a circular cross section. So what do you think? In which direction uh, the this column will buckle? So let's say this P is going towards critical load. So I am gradually increasing the load and it reaches the critical load. So if the load reaches the critical load, buckling should happen, right? So in which direction the column will buckle?
It can buckle in any direction, sir.
Yeah. So we don't know what it's like. There is every possibility that it can go in any direction and buckle because
Yes, sir.
we don't like there are a lot of things which we don't know, like the internal defects of the material, and also I while I apply the load, I might not apply exactly at the centroid of this cross section. I can have a slight eccentricity, like a point, slight like a centimeter or a like of eccentricity also uh, will lead to buckling in some direction. So things, a lot of things are not in our control. It can buckle in any direction. and the we have seen that we have seen the equivalent length or the effective length, right? So we have the critical load, which is equals to uh, what do you say, pi ei by pi square ei by l e square. So this is the equivalent length for pinned. What is this L?
Sir, two times, sir. Not two times. L is equal to L only, sir.
L is equals to L. L is equals to L. Effective length or the equivalent length is equal to L.
Same, yes, sir.
When I go to a fixed case, it is 2L. Sorry, L by 2.
Yes, sir.
And I think for what is uh, pinned and fixed and pinned case, this is I think 0.7, I guess.
Forget, sir.
Yeah, just like 0.7 and 0. I'll just see.
Yes, sir. 1 by root 2, no, sir.
1 by root 2. Okay, we'll just see. Just check.
Yes, sir. Correct, sir. 0.7. L by root 2. What Professor told. That time it will be 0.7.
Okay. So these are the things which we have learned. So this is called as Euler buckling formula. So we have seen the derivation and all. So we have taken the deformed configuration, Euler buckling formula. Okay. So buckling is a very, here we are only studying uh, the stability and all those things. It is like a buckling is more complex phenomena. It's actually a non-linear phenomena. That's why we take the deformed configuration and all. So we don't go in this course to non-linear things, and that is beyond our control. So we are just seeing the critical loads. Okay, stability of the columns. Okay, let's say I have uh, three some cross sections like this. One cross section is this. I have B and B. I have the other cross section this. This another cross section like this. Let's say this is Z and Y. Z, Y. This is again dy 2 and 2. I have a hollow section. This is only the inner is root 3b. Okay. This is entirely you can consider this as a section, square section, square hollow section. So for a pinned column, if I take any of these cross sections, uh, which column will give me the maximum load carrying capacity? So for a pinned case,
Sir,
yeah,
D first.
what you have to find out, what thing you have to
The
get,
moment of inertia, sir.
yeah, moment of inertia you have to get. So which one has the maximum moment of inertia? So I don't want any direction or something. I just want which gives the maximum load capacity. So this and this both are same. So you can find out BD cube by 12 like obviously if I find out I and IYY and IZZ, I can find out this. For this I can find out IYY or IZZ both will be equal. For this I have to both of them will give me like IYY and ZZ same thing but in a different orientation. But I don't want in which direction it will buckle or that. So same cross section but in a different orientation doesn't make any difference. So we have to find out all the uh, moment of inertia, and obviously if I compare this and this, you can see that the material is like more away from this uh, what you can say centroid compared to this. Well, let's say I'll just find out why am I BD cube by 12 or here you can say B into D cube by 12. First, let's say IZZ. So B power 4, oh yeah, 48. Okay, IZZ. And if I take IYY, 8B cube by 4, 4, 3. So B power 4 by 3. Okay. So this is uh, this is IYY. For this, if I take IYY or IZZ, both are equal. Let's say. So I have 2B into 2B cube by 12 minus root 3B into uh, root 3B cube by 12 uh, to a 16. Okay. 16 B power 4. And I will get 9 to 3 into 3 27 B power 4 by 12. Oh, why am I getting minus?
Sir,
Yeah, yeah.
it should be 9, no, sir. Root 3.
Yes, sir.
Yeah, yeah, okay. 3, 3, 3, yeah, 9, 9. Sorry. So I'll get 16 minus 9, I'll get 5 d power 4, 5. So, so this is obviously greater than everything else here. So, can say 5 by 12 is how much? 0.4166 d power 4, and 1 by 3 is 0.33 d power 4, and 1 by 4 is 0.25 d power 4, and this is 1 by 12, so lesser than this thing. So this gives me the higher moment of inertia. So obviously it makes sense to use this. So this I have the Euler buckling formula, right? So if I have higher I, I'll get higher critical load. So I can go to a higher load and my column will not buckle. So like if I have, let's say, different end conditions, uh, let's say first case is both ends are hinged, and the next case is both ends are fixed, and the other case is one end is hinged and one end is fixed, and the other case is one end is fixed and the other end is free. uh, which one will have the maximum critical load? So same column but different end conditions. So which one will be able to resist more load?
Both end fixed.
Yeah, both end fixed will have more, will resist more, what you can say, more load, because effective length will be less for the fixed case. Uh, Equivalent length will be less. So if I have less, equivalent length is less. If my equivalent length is less, obviously this is inversely proportional. My critical load will increase. So more load carrying capacity.
S- Sir,
Yeah, yeah,
sir, like in the previous, like in the third one, sir, which you did, we got I Z Z and I Y Y different, no, sir.
yeah, yeah. Different.
To
Yeah.
B and D. So, here we got uh, for I. Let's say that if I get less for I Y Y, so it means
Hmm.
it is buckling in Z direction. Is it correct, sir, to tell like that?
Oh no, no. Yeah, yeah. It is buckling in Z direction. Yeah.
Okay, sir. And
I'll just
plane,
show. Hmm.
yes, sir.
Yeah, yeah.
Then if plane is asked, like which plane, then
Which plane? Okay. So I have a column like this. So my orientations I will take like this. Okay. Let's say uh, this is x and this is y and this is z. Okay. So cross section is present in the xy direction. So so on the above, the moment of inertia about the x-axis is lesser here. Okay. Ix-axis is lesser than Iyy. So my column will buckle like this in this. Can you imagine it? Yeah, the column will buckle like this. About
Yes, sir.
about y-axis, sorry, about x-axis, it will buckle because moment of inertia is less. It cannot, like, obviously it doesn't make sense. You can just imagine also. So it will be stiffer in this direction. So it cannot. Uh, Bending in like this is very difficult because the moment of inertia is. Uh, Sorry for the horrible diagram. So bending like this is difficult, whereas bending like this is easier when I apply load because moment of inertia is less. Okay, when this bends like this, we can say that this is uh, if I look uh, like this, you can say that this is bending in mm, YZ plane. It is bending about x-axis, right? So you can say that this is bending in YZ plane. When it bends like this, you can say that this is bending in XZ plane because this is my plane, right? So instead of this, I'll just take the column like this. So if it is bending like this, obviously this is a 2D projection. I'm just taking of the column. Bending in X and Z direction, X and Z plane, bending in X and Z plane. Let's say if I look it from the sideways, I'll have the strip like this, right? Small dimension. So this is Y and Z. So it will bend in the YZ plane. Okay.
Okay, sir.
Mhm. Okay. So I'll just ask a true or false kind of thing. Let me know if it is true or false. So in design, the factor of safety is defined as the ratio of design stress to the yield strength, and it is usually less than 1. Is it true or false? Factor of safety, I'll just write. Factor of safety is ratio of design strength to the yield strength of the material. Design stress to the yield strength of the material. Is it true and it is less than or equal to 1? Is it true or false?
False, sir.
Yeah.
Yes, sir.
This is a false statement or a false equation because factor of safety we take as the ratio of yield stress to the design stress. Okay. And it is always greater than 1. Greater than or equal to 1.
Sir,
Hmm. Yeah.
sir, I have one doubt, sir. In this column problem, sir,
Hmm.
what is the radius of gyroscope, sir?
Radius of gyration is nothing. This is you can say that is one imaginary quantity. Okay. Radius of gyration is let's see, moment of inertia. Whenever we take moment of inertia, we calculate something, and moment of inertia is generally defined as this area moment of inertia is defined as area of the cross section into radius of the radius of gyration square. Okay. So and this okay, you can say if I want to find out the radius of gyration, like let's say for a triangle, uh, let's say for a rectangular section uh, or a square section, let's say I have b power 4 by 12, and I know the area for a square is b square, and I have r square. So if I do, I know a and also I know I. So I get b square by 12, and this is uh, r is root of this thing. So this is my radius of gyration for a square section. So radius of gyration is not a physical thing. Uh, you can just let's say you can just imagine like if I take all the material of the square and put it at a distance of r uh, from the axis from the axis from which I am calculating the moment of inertia, area moment of inertia. If I put all the area at a distance, all the area at a distance of r, then I'll get this moment of inertia equal to the moment of inertia of the section which we have. So b power 4 by 12. It's like it's like just you can say an abstract thing or an imaginary thing. So you can say average distance of all the particles of the section, uh, not an average, but you can say in a sense it is like an average distance of all the particles which are present uh, of the cross section which are present from the axis about which we are calculating the moment of inertia.
Sir, the same thing we can calculate by the parallel axis theorem, na, sir. The from a definite distance of axis, we calculate the moment of inertia.
No, no, parallel axis theorem is different, and radius of gyration is different. I will explain. Okay. See, parallel axis theorem is when, let's say, I know moment of inertia about this axis, which is passing through the center of my rectangle. But
Yes, sir.
I want to know the uh, moment of inertia about this axis. Okay. I know this, but I don't know this. Let's say if I have this, I can calculate this uh, by using the parallel axis theorem, which is I have, let's say this is Ix and this is some Id. Let's say Id is equals to Ix plus area of this cross section into the distance between two axes, which is let's say H here. This is parallel axis theorem. So I want to get the moment of area moment of inertia at an axis different from already which we know, like moment of inertia about some axis we know, but we want to shift it to other axis. So this is parallel axis theorem.
Yes,
Radius
sir.
of gyration is something like I have this square, right? I'll just explain like this. I have this square. Okay. So moment of inertia is nothing but a into r square, right? So I take small section, small elements, small elements like this. What we do, uh, so and these are present at a distance something from the axis. Okay. I don't know. Some r. Okay. This r is varying. So sum of all the small sections areas and sum of all these distances will give me radius of gyration. Okay, sorry, not radius of gyration, moment of inertia. Did you get it? Like it is like an average. Let's say I have a square. Let's say instead of the square, I'll convert this. I'll throw all the material of the square away at a distance r from this. At a distance r from the axis. So now if I multiply this area and the area of these strips are the area of these strips is equal to a. So it's like an average distance. So here my elements are present at a varying distance, right? Let's say if I assume that all my elements are present at a distance equal distance from the axis, that is r.
Understand, sir. Sir, that one doubt, sir.
Yeah.
Previously, sir, you told that if we know the moment of inertia, so it is in case of beam and column, whatever. So it is easy for us to understand that in which way it is give resistance to bend, or in which way it is give less resistance to bend.
Yeah.
So there is a significant edge there. So when if know the moment of inertia about the axis, we can visualize. So, but what is the significance of to know the radius of the gyration? Then what we can assume, sir? Means,
Yeah. See, what radius of gyration is simply saying you that the material, how much distance the material is present from the axis about which you are calculating the moment of inertia. If my radius of gyration is more, then it means that my material is more away from the uh, more away from the radius of more away from the axis which I am taking. Then it means that if r is more, let's say if you have two cross sections, okay, if you have two cross sections, different cross section, let's say one square cross section and one rectangular cross section, but they have the same area, but their radius of gyrations will be different. Let's say I take about this axis, radius of gyrations about this axis, I am taking this axis, okay. Radius of gyrations, area is same, but the radius of gyrations will be different. For this, the radius of gyration will be more. Why? Because you can see that the material is more material is at a greater distance from the axis compared to this square cross section. The square cross section is having the material uh, closer to the axis compared to the rectangular cross section.
yes,
Okay.
sir. Yes, sir.
So radius of gyration is, if the radius of gyration is more, it means that moment of inertia is more
Okay. Okay, sir. Understand, sir.
for
Yes.
a particular area. If the area is same, if the radius of gyration is more, it means that more material is present away from the axis about which I am calculating the moment of inertia. And if more material is present away from the axis, it means that it will give more resistance to bending.
Understand, sir.
Okay, that is the significance of radius of gyration. Or you can also simply you have also learnt uh, what do you say, mm, rotational inertia, right? So if you stand in the middle of a spinning thing, uh, you will have more speed, but if you go away from that, your speed will decrease.
Yes, sir.
uh, how to explain that, what do you call?
Sir, the conservation of the momentum, sir.
Yeah.
Understand, sir.
Yeah.
Yes, sir, sir. Understand, sir. So it is
Okay.
generally talk about how far your mass is distributed from the axis or.
Yeah. that is what we are talking. If it is present away, then it will have more resistance. Like that.
Understand, sir.
Let's say I do a final thing. If I have one strut like this, it is pinned here, pinned, and also pinned here, and this strut is there, and say this is making an angle of 45 degrees. And if I apply a load here, P, and what is find out the expression for load P for which the strut starts buckling. So first we have to find out what is the axial load uh, which we are getting due to the applied load P here. So we know this, we have learned in trusses and all. And just use the method of joints. Say this is FAB and say this is reaction B. So and this is 45 degrees. So I'll get FAB cos 45 minus cos 45 equals to P. So I'll get FAB is equals to minus root 2 P. Okay. Compressive force will be I have taken away. So initially I'm assuming that there is tensile force present in our, but we are getting the compressive force here. So the critical load, let's say I'll just take the magnitude, okay? I don't need plus or minus because I know it is compressive. So FAB is equals to root 2P. So I want to find out the maximum P which I can apply. So if FAB reaches the critical load or the buckling load, so buckling load for the pin case is pi square EI by L square. Let's say my length of the column strut is L, okay? Okay, pi square EI by L square. Then P will be equal to pi square EI by 2L square. This is the maximum P which I can apply. If I apply the load beyond this, sorry, this is root by root 2. If I apply the load beyond this, my column will start buckling. My strut will, the strut here will start buckling. So this is the maximum P which you can apply. Okay. Okay.
Yes, sir.
Okay. So any other questions? We'll stop here. The time is
No,
up.
sir.
Maybe I think, yeah. Priyanka, you were asking something.
Sir.
You were asking something.
Yes, sir. Actually, not regarding the subject, sir.
Hmm.
Actually, you mentioned about the MS program in IIT Madras, sir.
Yeah, yeah.
I had applied for the program,
Hmm.
and they have called for interview for this month end.
Okay.
So, like, interview means will it be like difficult or how? So,
No, nothing will be difficult. Okay. So I would suggest since you prepare two subjects. Where you have applied, like in which department or section?
Solid mechanics and fluid mechanics, sir, in applied mechanics department.
Okay. So you have applied for both of the things, for both groups. So uh, important thing is prepare strength of materials. Strength of materials is solid mechanics things. You have to uh, uh, they'll ask you questions on strength of materials. Apart from that, you have engineering mathematics concepts you revise. So not maybe like linear algebra, things like that, whatever you have learned in engineering, not probability and statistics, all those things, linear algebra and little bit of calculus and um, graphs. You should like different graphs, log x graph, e power x graph, these kind of questions they might ask. Uh, Sin x graphs, sin x, cos x, tan x, uh, elementary graphs like, or also y is equals to x square, x is equals to y square. So these things, and yeah, engineering mathematics, strength of materials, and yeah, and you can prepare another core subject of mechanical engineering which you might like. Maybe I don't know, like you can machine design or uh, something like that you can prepare. But major questions you can expect, like whenever first they'll ask you to introduce yourself, and they'll ask you what have you prepared for the interview. So they'll ask you what have you prepared. Then you can tell that, sir, I have prepared these subjects. Let's minimum two subjects you have to prepare, but like mostly you can expect like engineering mathematics and strength of materials. Solid mechanics, for that you have to prepare strength of materials. For fluid mechanics, again you have to go through fluid mechanics, I guess. Uh, so prepare according to that, and they'll start asking you questions like from basics. They'll ask questions. They will not go like very deep into things. So mostly you can expect questions from things which are very confusing, like the Moore circle and stresses, these kind of things. They can ask you, they'll give you a cantilever beam, and some moment is applied, some load is applied. Draw the free body diagram, and then you can, then they might ask you to draw the bending moment and shear force diagram, and then they can ask, then they can tell you, then they can give you different points on the beam. uh, then they can ask you to draw the stress state, how it is happening, how it is occurring. uh, all those different kind of things you can experience. Like you have, if you take an element at the neutral axis, there will be only shear stress, bending stress is zero. If you take the extreme fibers, you get only the bending stress. So these kind of things you can expect, like things, more circle, all these things, deflections and all. Uh, yeah, all everything is basic. Like so, initially, if they ask something, if you tell something, they'll ask you. Uh, they'll go again a little bit deeper on that, like more basic things they might ask you. They'll go a little bit deeper. If you don't know, just say that, okay, just try, just like if you don't know at all, just say that I don't know. If you know a little bit, uh, and you want to try, just you can, like say, you can start like, you can say that I want a moment, and just you try to recollect or write or do something, and then you can tell. Do no need to like hurry, like you don't need to be prepared with answer every time they ask a question. You don't need to uh, go in a hurry and let blur out. These are the things which I have done mistakes in interviews and all. So that's what I'm saying, like we don't need to hurry. So you can ask for a second or a minute to recollect things, and you can say. Again, if you don't remember anything or if you don't know the concept, don't bluff in the interview. Don't bluff. If you don't know anything, just say that I don't know. If you say that you don't know something, they'll ask you questions from something else. Okay, bluffing and saying some weird answers will make a bad impression. So we should avoid always doing that. And yeah, so the like you have to satisfy